Hello everybody, my name is Ahmad Issam, and in this video I'll introduce Polychase, a free and open source alternative to GeoTracker for motion tracking in Blender. Whether you are a VFX artist or just curious about how object tracking works, this video will walk you through what Polychase does and how it works under the hood. And by the end of this video, you will know how Polychase is capable of achieving a tracking result like this in a short amount of time. Here is what we'll cover. First, I will give a quick overview of motion tracking in Blender, what it is and how it works. Then we'll dive into what Polychase is and how it compares to the classical pipeline in Blender. Finally, we'll get technical and explore how Polychase works internally. Let's start with the basics. Motion tracking is the process of analyzing how objects or cameras move in a video. Typically, it involves 3 steps. First, we detect distinct features in the frames. These are usually edges or corners in the video. Then we track these features across multiple frames. And finally, we solve for the camera poses and 3D point positions that explain these 2D tracks. This is an example in Blender for the result of feature detection and tracking. Then the motion tracking solver takes those 2D tracks and tries to find the best explanation for them in 3D space. Specifically, it estimates camera or object poses, depending on what you're tracking, alongside 3D point positions in a way that minimizes reprojection error. Reprojection error is a term that we'll be using a lot in the next slides. This diagram shows an example of what we're talking about. Given a 2D track, here marked by the red point in each frame, we try to find the camera poses and the 3D position, which is marked as a big red circle, that minimizes the reprojection error. The reprojection error is computed by projecting back this red point into each frame, which is marked by the green circles. And the reprojection error is the distance between the true or the detected 2D feature and the reprojected 3D point. Actually, this setup has multiple variations. If we only know the 2D tracks, it's usually called bundle adjustments. And our job is to find both the 3D poses of the cameras and the 3D positions of the points. But if we know the 3D points already, this problem is called PNP, or perspective in point. Here our job is only to find the 3D poses of the cameras. If, however, we have the 3D poses of the cameras and the 2D tracks, then this problem is called triangulation. And our job is to find the 3D position of the points. Here is the same video, but now instead of just visualizing the tracks, we've inserted a 3D cube. Since we have estimated the camera motion mostly correctly, the cube stays glued to the scene, which is the basis for all kinds of VFX tracks. Blender's motion tracking is powered by a library called libmv, originally written by Kieran Merle. Sorry if I'm pronouncing his name incorrectly. It uses the Harris corner detector to find good tracking features and a variant of KLT tracker to follow them across frames. And then it applies a technique called bundle adjustment to find the camera poses and point positions jointly. If you are curious about what really happens, there's a great write-up called Open Source 3D Reconstruction from Video by Kier that dives into the details. Now here is a different scenario. What if we already have a 3D model of the object we're tracking? In that case, we don't need to reconstruct any points. They are already part of the mesh. All we need is to estimate how the camera or the object itself moves relative to the scene. This is actually what we just called before the PNP problem. And this is what Polychase is designed to do. So what exactly is Polychase? It's an open source alternative to GeoTracker by Keen Tools. GeoTracker is an incredible tool that many VFX artists already know and love. This project is just a re-implementation of that idea, but made free and open source. All the credit for the original concept goes to Keen Tools. Definitely check them out at their website. We make 2 core assumptions. First, you already have a 3D mesh of the object you want to track. The more accurate, the better. And second, that object is rigid, meaning it doesn't bend, squash, or deform. It merely translates and rotates. These assumptions simplify the tracking problem and allow for very fast and accurate results. The general workflow looks like this. Step 1. Analyze the video to extract motion features. This is done automatically by our tool. Step 2. Manually align your 3D mesh to the object in the footage. Step 3. We track forward or backward through time. And step 4. If the mesh drifts, we correct it at select keyframes using manual alignment. Step 5. And finally, we refine everything automatically to adjust the motion in between. It's a mix of automation and user-guided correction. In the video analysis step, we generate sparse optical flow data and store them in a SQLite database. And this is how we set up our scene in Blender. First, we import the mesh. Here it's a Herbie the Love Bug from the movie. Then we create a tracker, select the geometry, select the camera, and choose the clip. I'm just rotating the mesh to look at the right direction. And then we choose where we are going to save the database file, which will contain the optical flow data. And finally, we start analyzing the video. I'm speeding up this portion of the video here, but this is how it usually goes. Now that we have analyzed the video, our next step is to align the mesh to match the object in the footage. This can be a bit tricky, but Polychase includes a bin mode that helps you stick points of the mesh to specific locations, which makes alignment much easier. This also depends on the accuracy of the model and the estimated focal length and intrinsics of the camera. In this video, I'm showing how to align the mesh to the footage. First, I set the focal length, since I know it's about this value. Then I go into bin mode, and I start creating and dragging bins to align the mesh to the footage. This mesh is not actually very accurate, so we'll have to make some concessions, as we will not be able to align it perfectly, but it's good enough. Aligning the handle, aligning the back, and I'm speeding up this portion because you can see the idea. And here we go. And here I'm showing another important feature, which is masking. By pressing M, I'm going to mask parts of the mesh that, if tracked, will contribute negatively to the overall solution. I'm covering the windows because they are transparent and they will track what's behind them. I will also mask the parts of the mesh that are not accurate. For example, the back of the car and the front of the car. And I'm also masking the wheels because the wheels will spin and this will confuse the tracker. Now that we have aligned the mesh, we can use the automatic tracker to move forward or backwards through the timeline. If the mesh drifts away from the object, we can simply stop the tracker, correct the pose using bin mode again, and then run refinement to refine what we have already tracked. A video speaks more than words, so in this video I'm showing how this is done. First, here I clear the bins and just add some landmarks that I will remember, just to make sure as we are tracking, the bins stay in the same place. These bins are not actually used in the tracking whatsoever, they're just visual aid. Okay, now that I have added the bins, I will start the tracking process. This is actually how fast this is. This is not sped up. So we are tracking forward. And we are done. As we can see, the mesh has already slipped. So we'll be fixing it. And okay, this part of the video will be sped up. as I will be showing the constant realignment, refinement, and tracking. Okay, now that I have fixed the last frame, I'm going to refine the entire segment. We define a global cost function and we aim to optimize it. Now we're running the flip again to detect where the mesh drifts. It's mostly good. And okay, I'm fixing it again here. Refining in the segment on the right, and now refining the segment on the left. Testing the waters again. Again, refining on the left and refining on the right. And this is our final result. Of course, it's not perfect because the mesh is not perfect at all, but it's good enough for the purposes of this demo. And now that we have shown the demo and how Polychase works from the outside, it's time to lift the hood and see how it works from the inside. At its core, it relies on three key components. First, the perspective endpoint problem, or PMP. Second, optical flow, which helps track movement across frames. And third, the factor graph optimization that happens in the refinement step. So let's start with PMP. PMP, or perspective endpoint, is a classic problem in computer vision. It asks, given a set of 3D points and their 2D projections in an image, what's the pose of the camera that produces them? In many ways, Polychase is just PMP but on steroids. PMP revolves around three ingredients: 3D points on the object, their corresponding 2D positions in the image, and the camera pose that produces them. The goal is to find the pose that best projects the 3D points back into the 2D image, minimizing the reprojection error between the actual 2D points and the projected ones. Mathematically, this is what we are minimizing. The reprojection error is the sum of squared distances between the projected 3D points and their known 2D locations. The projection depends on two things: the camera intrinsics, things like focal length and principal point, and the extrinsic pose of the camera, which defines how the camera is positioned relative to the object. And in this visual, we show two 3D points, how they are projected, and the error we're trying to reduce. Now remember BIM mode? It's essentially an interactive way to define PMP problems. Each bin corresponds to a 3D point on the mesh, which we get through ray casting. That 3D point is then projected into the image to get a 2D point. When you drag a bin, you are changing its 2D position, which introduces a reprojection error. We can then solve a PMP problem to update the object's or camera's pose so that the new 2D point lines up better. Here is what that looks like in practice. Each time we drag a bin, we are triggering PMP optimization behind the scenes. When we have only 3 bins, there is an analytical solution to this problem, and we can minimize the reprojection error to virtually 0. As you can also see, when we click to create a new bin, we cast a ray from the camera center into the mesh, and the intersection becomes the new 3D point. But what if we are tracking a geometry and we want to adjust its position, not the camera? This is actually the exact same problem. What we care about is the relative pose between the geometry and the camera. We can either apply the update to the geometry or the camera as long as the relative pose remains the same. Tracking in Polychase is built on the exact same principle, but instead of manually placing pins, we generate them automatically using optical flow. For every frame, we estimate how key points have moved and used those as 2D, 3D correspondences. Then we run a PNP solver to update the pose just like before, but fully automated. Now let's take a moment to talk about optical flow. Optical flow is what gives us an idea of how things are moving across frames just by looking at pixel intensities. Now technically what we really want is the motion field, which is the actual movement of objects in the scene. But because we don't have full 3D knowledge upfront, we use optical flow as an approximation. The difference between optical flow and motion fields become clear if we are thinking about laminar flow of fluid, for example. In laminar flow, the fluid seems as if it is not moving, so optical flow would not detect any change in pixel intensities, but in actuality, the fluid is moving, but it's moving in a very regular fashion. So it's very important when we do optical flow that we track the movement of pixels that are not textureless, so preferably edges and corners. And here is what sparse optical flow looks like. Each arrow represents the motion of a tracked feature between frames. These arrows give us the data we need to infer how objects are moving, even when we don't know their full 3D structure yet. For our use cases, we use an off-the-shelf optical flow pipeline provided by OpenCV. First, we use the Shitomacy corner detector to find good features to track, which is done by the function cv good features to track. Then we apply a KLT tracker to track these features, which provide us with a sparse optical flow. These are widely used and reliable algorithms that form the basis for our automatic bin generation. Here is the general strategy. For each frame, we first detect a set of good features. Then we compute optical flow between that frame and its neighbors, not just adjacent ones, but also several steps away. This makes tracking more stable and robust. Now let's assume that we are forward tracking frame in. Let's further assume that earlier frames are already tracked. So we use optical flow from those previous frames into frame in. For each of those earlier frames, we collect 3D points by raycasting the tracked features onto the mesh. Then we get the corresponding 2D positions in frame in from the optical flow data. Finally, we run a BNB solver to estimate the pose of frame in, just like with manual bins, but fully automated and by relying on multiple previous frames. And now let's switch our attention to the refinement process. At this stage, we take all the tracked frames and observations and optimize them jointly using a vector graph. A factor graph is a bipartite graph with two types of nodes, variables and factors. The variables are the things we are trying to estimate, in our case, camera poses. The factors are constraints between them, derived from measurements like optical flow in our case. This structure is widely used in SLAM and 3D vision systems, and it's what Polychase uses for refinement. And since, as we said before, that the camera poses are the variables and the optical flow pairs are the factors, the optical flow diagram that we showed before is exactly the same as the factor graph that we are trying to optimize. You might ask yourself, how is this graph a bipartite graph? It's not bipartite at all. That's because we omitted drawing the factors. So in every edge between two frames, there is actually a factor in between. So frames are connected together through a factor, and this factor represents the cost function of the optical flow. And here is how we define the error or cost for each flow constraint. For each pair of frames, say frame I and frame J, that have a factor in between them, we take all the 2D points in frame I that have predicted 2D points in frame J from optical flow data, and raycast them into 3D using the mesh and camera parameters. Then we project the 3D points into frame J using its pose. The error is then the difference between where the points have landed into frame J and where the optical flow actually says it should be. By minimizing this reprojection error across all frame pairs, we get globally consistent motion. Interestingly, the optical flow error is exactly the same as the BMB error, with one key difference. In BMB, we assume the 3D points are fixed and known. But with optical flow, the 3D points are not fixed. They depend on the pose and intrinsics of the source frame. And as we optimize the poses of the frames with iterations of optimization, these 3D points are changed accordingly. We can actually use this information to get a better Jacobian by differentiating the error through the source and target frame, unlike the error in BNB, where we only differentiate the error through the target frame and we assume the 3D points to be fixed. Despite all these constraints, the resulting vector graph is still extremely sparse. And as we have seen in the previous slide, the error is actually a summation of square terms. So this lends itself nicely to the machinery of sparse nonlinear least squares problems. This sparsity carries over into the optimization, making the system fast to solve even with many frames. Here you can see the sparsity pattern of the approximation. It consists of 8 diagonal lines corresponding to the 8 connections of each frame. There are actually a lot of details involved in making this optimization work, like the use of robust loss functions and reweighting factors based on how near they are to ground truth variables. But we'll leave that for another time. There is a lot of room for improvement. We are missing a lot of small features, such as 2D masks. I want to try experimenting with dense optical flow and dense optical flow neural networks to see how they differ from the classical optical flow solutions that we're using. And we can actually also support deformable meshes. For deformable meshes, we won't be optimizing only the global pose, rotation, and translation. We will be optimizing the global rotation and translation alongside with the rotation and translation of each joint. When I first started with this project, I managed to get a demo working for bin mode and tracking very quickly. The issue was with refinement, as it was beyond my mathematical knowledge. These resources helped me immensely. First, I decided to write the iterative BNB algorithm, and I understood how to do that thanks to PoseLib, which is a library for minimal solvers for camera pose estimation. Then I looked into TinySolver by Keir, which is a small library for solving nonlinear least squares problems. Both of these libraries helped me understand how nonlinear least squares problems are implemented, but they did so for dense problems, so there was still some work to do to write a sparse version. And in all of these trials, I always had the paper, bundle adjustment, and modern synthesis with me to understand the mathematics behind the code. Thanks for watching this presentation. You can get the code at the link in the slide. I also leave the link in the description. And see you with another project.